Before we send you off to start learning about the pipeline, we thought we would point out a couple of things for you, some resources, and we'll also talk to you a little bit about the data products that go into and come out of the pipeline. So I'll talk to you about data that you can expect to find in MAST, and then we'll take a quick look at the exposure format and metadata using Astropy tools, and then we'll wrap up this quick presentation by switching to talk about an important tool called JWST data models. So there's a lot of resources at your fingertips if you have any questions while you're going through this process. The first one is the JWST help desk. There are a lot of frequently asked questions and knowledge base articles for you. If you have questions, you can search through those. If you don't see answers that you need, you can always submit a ticket using the Get Help option, and you can select the card that is associated with your question. I'm also showing you a link to the MAST website for the Mikulski Archive for Space Telescope. This is where your JWST data is going to be one day. And that is the landing page that will provide you with announcements and also links to the data portal. One of the most important resources for you is going to be the JWST user documentation. Some of you might be familiar with this already if you were working on JWST proposals. But there's also a section for JWST data products and understanding data files in the pipeline. For those of you who want more in-depth information about the JWST pipeline and all of the associated things like the data products, you can dig into the software Read the Docs. This is software-focused documentation that's stored within the pipeline repository itself. So it's the most up-to-date resource for you, and it contains the most details on the pipeline. And finally, all of the information in these slides were extracted from the Pipeline Products webinar. So if you want more information or more in-depth examples, you can visit that website in order to grab the materials or the recordings from the first session. Let's get started. There are a lot of different modes and instruments for JWST, which means there's a lot of different data products that you'll find in MAST. You can visit the MAST documentation for more information about the standard data products that you can find. Of all of these different products, most of you will probably find that the science data files are sufficient for your analysis, but you can also access things like guide star data or association tables. So the standard science data files that you'll find in MAST are the uncalibrated raw data. This will be identified by the suffix uncal in the file name. This is data that has not been sent through the calibration pipeline yet. You'll also see count rate data. These are slope images that come out of the stage 1 pipeline. All of the detector level corrections have been applied, and the suffix for these files will be rate or rate ints. Rate ints is going to be for integration specific data products versus the rate file, which is integration average data products. Next up, you'll also see calibrated single exposures identified by cal or calints.fits. And then out of the stage 3 pipeline, you'll see resampled or combined exposures. And these are I2D or S2D.fits, depending on if you have imaging or spectroscopic data. And for those of you who have spectroscopic data, you'll also see the extracted spectra. And these are going to be in X1D or C1D files. So click on those links for more information. And now let's start talking about the format of your data. So in this slide, I'm showing you the information about the standard extensions that you'll see in your data products. These are FITS image or bin table extensions, and each of the extensions has associated headers. So the primary extension is going to contain most of the header keywords for your exposure. The science extension is where the good stuff is going to be. Your science data is in this extension along with science specific header keywords. The zero frame extension is for cases where you have grouped data or frames that get averaged together. The first frame will be saved separately for you as an extra data point. You also have group extensions and an integration times table included. And then finally, the ASDF extension is what helps the data model framework work with the FITS files, and that's where your WCS information is going to be. This is information that's extracted from the Jupyter notebooks from the first webinar. So here we're using the Astropy fits tools in order to take a look at an uncalibrated NearCam file. So here we read in this uncalibrated file and we take a look at it using fits.info. And here you can see the different extensions that I just mentioned, your primary, science, zero frame, group, integration times, and ASDF. And then on this side, you can see the shape of these extensions. So here, this reflects the 4 dimensions for this NearCam exposure, 2048 by 2048 pixels, 10 groups, and 1 integration. And then the zero frame extension, it's just 1 single frame saved out separately. So this shape reflects the up the ramp readout. This is the standardized readout sampling for all JWST detectors, and Carl Gordon will talk about that more in just a second. And then if you want to load up your science data, you can just grab the extension that you're interested in looking at and use fits.getData. The science data is in the first extension, so we say 1 here, and you can see that that reflects the shape that we show above. The header keywords, you can access those using fits.getHeader. So here we read in our uncalibrated file and we select the headers that we want to take a look at. When you're using the fits tools, you can search through the headers using the wildcard asterisk if you're not really sure what a header keyword should be. So for instance, if I want to search for all the header keywords with OBS in the name, I do OBS asterisk, and it pops up all of the keywords with OBS in the name for me. And then to access those, you just type in your primary header keyword name, and it prints that out for you. So here we have the observation ID, your instrument, and your exposure type. And the exposure type header keyword is what helps determine the path of your data through the calibration pipeline that indicates the observing mode. So that's taking a look at the data products using FITS tools, but now we're going to repeat the process using JWST data models. The JWST data models are a really important tool for working with JWST data and all of the software that we're developing at Space Telescope. A lot of our software assumes the use of data models. They are a framework to help insulate steps, pipelines, and us, the users, from some of the complexities of all these different JWST file formats. And it helps to make sure that we have consistency across all of the different software. So you can kind of think of them as a container for your data that you can drop your data into, and it performs certain checks like formatting, data types, and making sure that your data has all the expected headers so that it can interact properly with the software. So the data models have a standard set of arrays associated with all of them. It depends on the data model type, but in general, you'll see a science data array, some kind of data quality array, and then also an error array. So there's lots of different models. They're specific and general depending on the type of data you have. So for instance, for our uncalibrated observation that we were talking about a second ago, that's a FITS file that's compatible with the stage 1 pipeline, and it would use a ramp model. Instead, if you have a 2D JWST image, you would use an image model. And you can follow those links to get a full list of all of the different data models that we have. So here we show you by loading up the data model package what an empty model looks like. So in this case, this is a ramp model. And here we show you the empty container. So this is just the structure. There's no data inside of it, but you can see you have your data array, a pixel data quality array, a group data quality array, and an error array. None of these have a shape to them. This is just an empty model with no data. So the good news is you don't have to know what kind of model to use. The data model package can actually guess for you. All you need to do is datamodels.open and read in your file, and it will guess. It will take a guess at what kind of model it should be using. So if we repeat the exercise of looking at the format of our uncalibrated file, but this time we're going to load it into a ramp model or open it with the data model package. Now you can see that that container is no longer empty. So this has all been filled out based on the information that's in the uncalibrated file. You can see the data array. Now this data shape reflects the 4 dimensions that we saw before. You have your group and your integration times. All of those header keywords are in meta. Then you have the zero frame extensions and your pixel data quality and the error array as well. So one of the benefits of the data models is that they're very easy to search and easy to update. So there's several functions that are included in the data model package to help you search for different things. For instance, if you want to know all of the header keywords that contain the name target, you do .search schema or .search depending on the information that you want to find. If you do .search schema, it prints out all of the path to all of the information containing the name target. Or if instead you're trying to figure out what kind of data type you need for a particular keyword, you can use .search and provide a key. So here we're searching for any metadata with the name deck in it. And so here you can see it prints out and tells you also the data type that the software is expecting. So if you were to read in, for instance, a string instead of a float, the data model package will spit out a warning to let you know that's not the correct data type. You can also look at all of the metadata at once by doing model.meta.instance, and it prints out all of the header keywords for you, or just access one by printing the full name or the path to that within the meta array. As I mentioned, all of this was extracted from the notebooks for the first webinar, so you can always visit those materials in order to get a more in-depth exploration of the data products as they go through different stages of the pipeline.